Okay, in this video, we're going to go over a problem in inequality. Maximizing, minimizing problems are also considered problems in inequality. So it's an old problem from Putnam, but it is related to the topic of inequality, so I thought we could discuss that one. So we have n points on a number line, and we are trying to minimize the total distance of those n points to a given point. So what is changing is this point P, which could be changing, and the points P1 through Pn are given. So let me start with trying this as usual for different points, different number of points. So if I have one point P1, then clearly the only point that works is going to be the only point that is going to give us the minimum is going to be P. So P equals P1 gives you a minimum of 0. If you have 2 points, and they did mention that the points could be the same, so they're not necessarily distinct. So the point that you're taking, if it is in the middle, then the distance between P and P1 added to the distance from P and P2, that would be the distance between P1 and P2. And if it is outside of here, then it would be larger. So if you have a point Q here, this distance plus that distance would be larger than the distance from P1 to P2. So that means the distance, the minimum is in fact the distance between P1 and P2. And that is obtained by any point between P1 and P2. Okay, so now let's look at the case of 3 points. So it looks like the order does matter. Order of these points does matter. So let's see what happens if we have a point P. So in order to minimize the distance between P and P1 and P and P3, then I would basically have to put the P in between. So if I have the distance between P and P1 and the distance between P and P3, that is always greater than or equal to the distance between P1 and P3. So it seems to be best to place P in between P1 and P3. Now, that is nice because now I would have to make sure that P2 is minimized, and the minimum of that is just 0. So that means the minimum distance would be exactly P1, P2, and this is P1, P3, and this is at P equals P2 that is going to be obtained. So going back here, we see that the distance between 2 points for the n equals 2, the distance between the 2 points is the minimum. For n equals 1, the point should be on the point P1, and for n equals 3, the point should be on the point P2. So it seems like maybe, in fact, it is different from for odd and even numbers. Yeah, if n is odd or n is even. But let's see what we get for 4 points. So I'm going to think about it in the same way. If I have a point, I probably have to place it right here to minimize the distance between P and P1 plus the distance between P and P4. So that is greater than or equal to P1, P4. But at the same time, I want to also make sure that the distance between P2 and P and P2 and P3 and P is also minimized. And that is also greater than or equal to P2, P3. So in order to make sure that both of these two are satisfied, I need to make sure that my point is on this interval and also on this interval. So as we see, so P must be on the segment P2, P3. So anywhere on that segment gives you the minimum. Okay, so the contrast is quite clear now. we checked for n equals 1, it has to be the point. N equals 2, it has to be somewhere in between the 2 points. N equals 3, it has to be the midpoint, the point P2, which is like, I guess, the median of those points. And point, for 4 points, it would be somewhere in between the P2 and P3. So somewhere in the middle would have to be middle, as in counting them. If you count them, if you have 4 points, you have to go 2 on that side, 2 on this side, 2 from the smaller one, 2 from the smallest one, 2 from the largest one, and then somewhere in between those two would be your point. And if you look at 5 points, then it clearly the same story is going to hold. So you have P2, P3, and then P4 and P5. So you would have to place your P right here, because PP1 plus PP5, that's greater than or equal to P1, P5. And then PP2 plus PP4 is greater than or equal to P2, P4. And then PP3 is at least 0. So the minimum is at P equals P3. Okay, so let us write down the solution now. So now it becomes clear that there is a difference between odd and even. So here's what we're going to show. So first, let's just start with setting them in a certain order. So suppose x1 all the way to xn in this order are the real numbers associated with these points. If n is odd, then P must be the point associated with x sub n plus 1 over 2. It's just the midpoint. And if n is even, then P could be any point between x sub n over 2 and x sub n over 2 plus 1. Let's go back and see what their question is exactly asking. If it is asking for the minimum, or if it is asking for the point P, because that does make a difference. For what point P? So we just need to find the point P. So any point in between these would work. So you could say n plus 1 over 2 would always work. Floor of n plus 1 over 2, perhaps. So in particular, P equals x sub n plus 1 over 2 always gives us the minimum. Okay, so how are we going to do that? At this point, you could use either induction, or you could just say that, well, we'll take the 2 endpoints and then we'll repeat that argument. But I think induction would be generally a better strategy. So we will prove this claim by induction on n. For n equals 1, okay, I guess I'll say let x be a real number associated with P. For n equals 1, the distance between P and P1 is just x minus x1, which is greater than or equal to 0. And equality holds when P is P1. So that completes the proof for that. For n equals 2, the distance between P and P1 plus the distance between P and P2 is going to be x2 minus x, which is greater than or equal to x2 minus x1 by the triangle inequality. And equality holds when x is between x1 and x2 as desired. Okay. Now we're going to make two jumps because you have a different answer for odd and even. We'll have to do two jumps. Okay, so that's your basis step. Now, so now we're going to go ahead and do the inductive step. Okay, so what we know is that PP1 plus PPN is x minus x1 plus xn minus x, which is greater than or equal to xn minus x1. And the equality holds if x is between x1 and xn. Now, by inductive hypothesis, we know the sum of PPI I equals 2 to n minus 1 is minimized when P is at x sub floor of, so we have n minus 2 numbers, so it's n minus 2 plus 1 over 2. So I'm using that 1 point, and we know at that point it is minimized, which is x sub floor of n minus 1 over 2. Oh, in fact, it is, so I'll have to figure out what's the midpoint of these. So what I have is, I'll have to take that, and then I'll have to translate it by 1. So that's exactly n plus 1 over 2. Yeah, because the indices start from 2 to n minus 1. So I'll have to take n minus 2 because there are n minus 2 indices, and then add 1 and divide by 2, but then I have to shift it by 1 because all of the indices are shifted by 1. Okay, so this is minimized at that. And since x sub n plus 1 over 2 is between x1 and xn, the minimum for the entire sum I equals 1 to n PPI is for when P is at x sub n plus 1 over 2. And that completes the proof of this one.